Hello friends. In the previous lecture, we have discussed LMTD method for heat exchanger analysis. In this session, we will discuss another method for heat exchanger analysis, that is effectiveness NTU method. Before going into effectiveness NTU method, we must know why we need an alternate method for heat exchanger analysis even though we have LMTD method for the same. First of all, we will see when we apply LMTD method and what are the data requirements for applying LMTD method. LMTD method is a convenient method for heat exchanger analysis when outlet temperatures of hot and cold fluids are known and our objective is to find heat transfer rate and heat exchanger area. But if the task itself is to find out outlet temperatures of hot and cold fluids and heat transfer rate with type of the heat exchanger, fluid inlet temperatures, and mass flow rate of the fluids are specified, it is difficult to use LMTD method because in this condition, LMTD method requires tedious iterative procedures. In such a scenario, a relatively simpler and convenient method known as effectiveness NTU method is used. To be precise, when outlet temperature of the fluid is known, LMTD method is preferred. If outlet temperatures of both the fluids are unknown, effectiveness NTU method is used. Outlet temperatures of both the fluid means if we know a outlet temperature of any one of the fluids, then the other can be obtained by applying energy balance. That is why it is mentioned as outlet temperatures of both the fluids are unknown, we use effectiveness NTU method. In effectiveness NTU method, first of all, we should know what is effectiveness. Effectiveness is a dimensional parameter used to express performance of a heat exchanger. Effectiveness of a heat exchanger is defined as the ratio of actual heat transfer rate to maximum possible heat transfer rate. Effectiveness is represented by the Greek letter epsilon. Effectiveness epsilon is equal to Q by Q max, where Q is the actual heat transfer rate and Q max is the maximum possible heat transfer rate associated with the heat exchanger. If we know the value of effectiveness and Q max, you can calculate Q, which is the actual heat transfer rate. We know that actual heat transfer rate can be expressed as m dot Cp delta T of hot fluid, which is equal to m dot Cp delta T of cold fluid, which is given by equation 2. Once we know actual heat transfer Q, we can calculate exit temperatures of hot and cold fluid, which is our required solution. Now the question is how to get the value or how to evaluate effectiveness and Qmax, and this will be discussed shortly. Before going to epsilon and Qmax, let's have a discussion regarding the equation pertaining to actual heat transfer rate. Actual heat transfer rate is given by equation number 2, where m dot h is the mass flow rate of the hot fluid, m dot c is the mass flow rate of the cold fluid, both in kilograms per second. Cph is the specific heat capacity of the hot fluid. Cpc is specific heat capacity of the cold fluid, both in joules per kilogram Kelvin. Normally, the term m dot h into Cp or m dot into Cp appears commonly in heat exchanger calculation, so it is convenient to combine them to form a single term known as heat capacity rate, represented by capital C. Ch is heat capacity rate of hot fluid given by or combining m dot h and Cph. So Ch is equal to m dot h Cph, heat capacity rate of hot fluid. Similarly, if we combine m dot c into Cpc, we will get heat capacity rate of the cold fluid, capital C suffix small c, is equal to heat capacity rate of cold fluid. The unit of heat capacity rate of a fluid is watts per Kelvin. Mass flow rate unit is kilograms per second, and specific heat capacity of fluid is joules per kilogram Kelvin. So the unit of specific heat capacity of a fluid is kilograms per second into joules per kilogram Kelvin, which will be joules per second Kelvin. We can combine joules per second to watts, so it is watts per Kelvin. Now, the larger value of Ch and Cc is termed as Cmax, which is the maximum heat capacity rate. It can be Ch or Cc depending on the value of mass flow rate and specific heat capacity of the fluid. C minimum is minimum heat capacity rate, which is minimum value among Ch and Cc. Now, equation 2 can be represented in terms of heat capacity rates of the fluid. It's given by equation number 3, that is Ch into Th1 minus Th2 is equal to Cc into Tc2 minus Tc1. In this equation, if Ch is equal to Cc, then Th1 minus Th2 is equal to Tc2 minus Tc1. That is, if heat capacity rates of the hot and cold fluids are same, then temperature change experienced by hot fluid will be equal to temperature change experienced by the cold fluid. Or if heat capacity rates of hot and cold fluid are same, then temperature gained by cold fluid will be equal to temperature drop experienced by the hot fluid in the heat exchanger. If heat capacity rates of the fluid are unequal, that is, if heat capacity rate of the cold fluid is smaller compared to that of the hot fluid, then from equation number 3, we can infer that the temperature change experienced by the cold fluid will be greater compared to that of the hot fluid. Similarly, if the heat capacity rate of the hot fluid is smaller compared to that of the cold fluid, then temperature change experienced by the hot fluid will be greater compared to that of the cold fluid. So the point is that a fluid with minimum heat capacity rate experiences maximum temperature change in a heat exchanger. We have effectiveness epsilon equal to Q by Qmax. If you know effectiveness and Qmax, actual heat transfer Q can be calculated. Now let us discuss how Qmax or maximum possible heat transfer rate is determined. We will consider a counterflow heat exchanger to determine the maximum possible heat transfer rate. Why? Because under similar conditions, counterflow heat exchanger has higher heat transfer rate compared to a parallel flow configuration. In this view, let's have a quick review on counterflow heat exchanger and its temperature profile. Consider a double pipe counterflow heat exchanger. Hot fluid flows through the inner tube in one direction and cold fluid flows through the space between the outer and inner tube in the opposite direction as shown in the figure. Now, if we plot the temperature variation of the fluid along the length of the heat exchanger, that is, if we plot the temperature change of the fluid along the length of the heat exchanger, we can see that temperature of the hot fluid decreases from Th1 to Th2 in the direction of flow, and consequently the temperature of cold fluid increases from Tc1 to Tc2 in the opposite direction. For a counterflow heat exchanger, the maximum possible heat transfer rate occurs when the exit temperature of the fluid with minimum heat capacity rate becomes equal to the inlet temperature of the other fluid. This condition for maximum possible heat transfer rate occurs when the length of the heat exchanger is very large or infinite. We will discuss these 2 points in detail in the next slide. Consider a condition where the heat capacity rate of the cold fluid is less than that of the hot fluid, that is, C minimum is Cc. Now we consider the temperature profile for a counterflow heat exchanger with finite length. Then the temperature profile will be hot fluid profile will be like this and cold fluid profile will be like this. Now the heat transfer rate associated with this heat exchanger in terms of cold fluid can be represented as Q is equal to Cc into Tc2 minus Tc1. Keep it as equation number 5. Now we know that when the length of a heat exchanger increases, then the heat transfer rate also increases. And consequently, the temperature difference between the hot and cold fluid keeps on decreasing. When the length of the heat exchanger is made infinite, then the corresponding heat transfer is the maximum possible heat transfer, and at this condition, the temperature difference between hot and cold fluid approaches zero. Thus, if the length of the heat exchanger is made infinite, the temperature profile of the hot fluid will be like this. Since the cold fluid has minimum heat capacity rate, it undergoes larger temperature change, and the temperature profile for cold fluid for a heat exchanger with infinite length will be like this. Thus, for a heat exchanger with infinite length, the exit temperature of cold fluid becomes equal to the inlet temperature of the hot fluid, such that for a heat exchanger with infinite length, TH1 will be equal to TC2. Keep it as equation number 6. That is, exit temperature of the fluid with minimum heat capacity rate becomes equal to the inlet temperature of the other fluid. This is in line with what we discussed in the last slide. So, for maximum heat transfer rate, that is for a heat exchanger with the infinite length, Q becomes Qmax when Tc2 becomes Th1. So maximum heat transfer rate can be represented as Qmax is equal to Cc. Instead of Cc, Cc is C minimum. So Qmax is equal to C minimum into, instead of Tc2, we will put Th1. So Qmax is equal to C minimum into Th1 minus Tc1. This is the expression for maximum possible heat transfer rate. Now consider the other case where the heat capacity rate of the hot fluid is less than that of the cold fluid, that is C minimum is equal to Ch. If we consider the temperature profile for the counterflow heat exchanger with the finite length, then the hot fluid profile will be like this, cold fluid profile will be like this, and the heat transfer rate associated with this heat exchanger in terms of hot fluid will be Q is equal to Ch into Th1 minus Th2. Keep it as equation number 9. Now, for a heat exchanger with infinite length, the cold fluid temperature profile will be like this. Since hot fluid has minimum heat capacity rate, the temperature change experienced by the hot fluid will be larger, and for an heat exchanger of infinite length, the exit temperature of the hot fluid becomes equal to the inlet temperature of the cold fluid, such that Th2 equal to Tc1. That is Th2 equal to Tc1. Now, for a heat exchanger with infinite length, Q becomes Qmax when Th2 becomes Tc1. So from equation 9 you can write maximum heat transfer rate Q becomes Qmax when Th2 becomes Tc1. So Qmax is equal to C minimum into Th1 minus Tc1. Put it as equation number 11. From the expression 7 and 11, it is clear that irrespective of whether the hot or cold fluid has minimum heat capacity rate, the expression for maximum heat transfer rate will be same. That is, Qmax is equal to C minimum into Th1 minus Tc1. So we can conclude that maximum heat transfer rate is achieved when cold fluid is heated to the inlet temperature of hot fluid, or hot fluid is cooled to the inlet temperature of cold fluid. Thus, the maximum possible heat transfer can be obtained when 1. The cold fluid is heated to inlet temperature of the hot fluid. This happens when the heat capacity rate of the cold fluid is smaller, or when hot fluid is cooled to inlet temperature of the cold fluid. This happens when heat capacity rate of the hot fluid is smaller. In both cases, the equation for Qmax is same, that is Qmax is equal to C minimum into Th1 minus Tc1. That means if you know the heat capacity rates of the fluid and inlet temperature of the fluid, we can calculate Qmax by using this equation. Now we have the expression for maximum possible heat transfer rate. From the expression of effectiveness, actual heat transfer rate Q can be calculated from expression 13 without knowing the outlet temperature of the fluids. Once you know the actual heat transfer rate, the exit temperature of the fluids can be evaluated from equation number 14. Now, to perform all these things, effectiveness of the heat exchanger is required. Now we will discuss how effectiveness of a heat exchanger can be determined. Effectiveness is a dimensionless parameter used to express the performance of a heat exchanger. It depends on several variables such as geometry of the heat exchanger, that is area of the heat exchanger, flow arrangement, that means whether the heat exchanger is a parallel flow type or a counter flow type, overall heat transfer coefficient, heat capacity rate of the fluids, etc. Thus, it is difficult to represent effectiveness as a function of these variables in a single equation. So, we go for dimensional analysis where we combine these variables to form dimensionless groups as we did in natural and forced convection. By non-dimensional grouping, effectiveness of a heat exchanger is expressed as a function of two non-dimensional numbers. First one is number of transfer units, abbreviated as NTU. NTU is a non-dimensional parameter formed by non-dimensional grouping of U, A and C minimum. NTU is given by UA by C minimum, where U is the overall heat transfer coefficient, A is heat transfer area of the heat exchanger, and C minimum is the minimum heat capacity rate. From the expression of NTU, NTU is proportional to surface area of the heat exchanger. Larger the surface area, larger will be the size of the heat exchanger. So NTU is the measure of the size of the heat exchanger. Higher the value of NTU, larger will be the size of the heat exchanger. The next non-dimensional parameter is heat capacity rate ratio, represented by capital C. Capital C is equal to C minimum by C maximum. It is the ratio of the heat capacity rates in such a way that C minimum by C maximum, and that is why it is known as heat capacity rate ratio. The effectiveness of parallel and counterflow heat exchangers can be derived as a function of these two non-dimensional parameters, that is NTU and C, that is number of heat transfer units and heat capacity rate ratio. Effectiveness of parallel and counterflow heat exchangers can be derived by following the same methodology that we used in the derivation of LMTD. The only difference is that during the derivation, the variables will be grouped to form non-dimensional terms. If we group into non-dimensional terms, effectiveness can be represented as a function of number of transfer units, that is NTU, and heat capacity rate ratio, capital C. For parallel flow heat exchanger, the relationship is given by equation number 15, and for counterflow heat exchanger, it is given by equation number 16. From these equations, if you know the NTU and heat capacity rate ratio, effectiveness of the heat exchanger can be calculated. Now let's have an overview of effectiveness NTU method. Our objective is to find out fluid outlet temperatures and heat transfer rate. Available data are type of the heat exchanger, fluid inlet temperatures, and fluid mass flow rate. Effectiveness of a heat exchanger is defined as the ratio of Q by Q max, that is actual heat transfer rate, to maximum possible heat transfer rate. If you know effectiveness of the heat exchanger and maximum possible heat transfer rate, actual heat transfer rate can be obtained. Effectiveness of the heat exchanger can be expressed as a function of number of transfer units NTU and heat capacity rate ratio, capital C. And maximum possible heat transfer can be obtained from the equation Q max is equal to C minimum into TH1 minus TC1. Substituting the value of effectiveness and Q max, actual heat transfer rate can be obtained. Now, if you know the actual heat transfer rate, outlet temperature of the fluids can be determined. All the equations that we use in effectiveness NTU method, that is the equation for maximum possible heat transfer rate, effectiveness of the heat exchangers, NTU, all these equations are available in the data book. So it is about effectiveness NTU method. Thanks for listening. We'll meet in the next session. Till then, bye.